Hello again. So last time in previous video, I asked you to answer my question about the mean and median of right skewed and left skewed dataset. I asked you to answer this question about right skewed, which one is bigger, mean or median. But I forgot to ask you write down the reason also to explain it, why you chose either of these. And then similar to the second question, explain your answer and let me know what you think about this and why you chose either of them. Okay, so here for today, I'm going to continue drawing histogram. Now I want to use NumPy and Pandas, a NumPy package, to generate random numbers. Okay, let me do okay, do you remember how we can generate random numbers? Okay, so I want to create random numbers using NumPy random dot randn, and I want to create 1000 random numbers, negative and positive floats, right? Okay, so let's print this random numbers. These are all the random numbers I created. They are all floating numbers, right? Okay, I'm going to... So what I'm going to do here, I'm going to plot this. First of all, I'm going to say figure. I don't even need to create subplot because I can just create the figure and what's that? Assign a kind of size to the figures 6 and 5. Okay, for now let's do this and then later I will show you how to just use only figure size. Okay, let's create subplots in case we want to generate 2 of them. 5 DPI is 120, and then I don't need anything else. This is fine. So now we have an empty graph, and then using matplotlib, I'm going to create a histogram. So this method is now different. I use plt histogram, and I'm assigning my random numbers here, and I'm saying let's create 50 bins, and well, we can create a color, let's say red, and that's it. This is the graph we made. Well, if you draw a curve here, it seems a normal distribution or a symmetric distribution around 0, almost 0. Okay, these are random numbers, right? So every time I run this, we'll have a different distribution. Okay, pay attention to this middle part. This will change if I run it again. Look, it will change because these are random numbers, right? So how can I fix this, and how can I set it up the way it never changes? We can use seed. We can use np random dot, is that dot, seed, and then any number like 2020, 10, or any fixed number, constant number that you like. What this does, this will be to ensure we get the same random numbers each time we run this cell. So if you write this down before creating random numbers that you created will be always the same, because this number is always the same. If instead of 2020 next time I use 14, I will have another number, and then that random number will be generated on this seed, the number of seed you chose. Okay, so look at this. Still, I will get the same graph. Look at the top part of graph. Look at the numbers. Everything is exact same. Okay, so this is the way I try to generate random numbers and draw a histogram of those random numbers. So what this histogram says, we have all the random numbers from -3 to 3 something, right? And then I have 1,000 numbers, right? 1,000 random numbers. It says most of numbers, generated numbers, are repeated, the highest, most of numbers, sorry, around -1 to 1 are repeated more often. So, for example, numbers that are randomly chosen and they are like on this area, we have 50 or how many, 60 of them almost, right? And then how many numbers are around -3, maybe 3 of them, right? And then how many numbers are -2? Almost 8 or 9 numbers out of 1,000, right? So this is the way you can describe this histogram. The pattern is symmetrical, and then mean or median are around 0, right? And then we have almost 1 peak. Okay, so what else? Yeah, so it says more frequency is around these random numbers, -1 to 1, or you want to make it closer to 0, around these numbers. Okay, so what I want to talk about after showing this, I want to talk about the I want to talk about central limit theorem. Okay, what is central limit theorem? Okay, if you remember the second video I showed you, I was introducing this course to you. When they talked about wisdom of crowd, after that they talked about law of large number and central limit theorem. So what central limit theorem says, it says if you have a population of let's say people's height, right? And then in that population there is an average of height, right? So we call that average of population, average of height for that population. So let's say the population contains 1,000 or 2,000 people, And then we calculated the average of height for those 2,000 people. Okay, so this is the idea of what population means and what variable I'm talking about. So now, every time from this population, get a sample randomly, sample of size 20. Every time you get the sample of their height, you will have 20 heights. You will find the average for this sample, average of height in this sample. Then you will get another random sample out of population, calculate the average height. You will do this over and over and over, let's say 1,000 times. You will get the same size of sample from this population. Okay, if I do this, if I draw a histogram of the average of height for all these samples that I chose, what happens? The histogram will show a normal distribution shape, almost symmetrical, but it will be a normal distribution. So what this says, central limit theorem states that distribution of sample approximates a normal distribution, or that bell curve, right? As the sample size becomes larger. So as I said, if I take these samples over and over and over and over, let's say I take 1,000 samples, 1,500 samples, but the same size each time, assuming that all the samples have the identical size. Regardless of the population distribution, the average of these samples will become a normal distribution. Okay, so now it becomes a normal distribution with the same mean as the population mean, and the standard deviation will change a little bit. Okay, so that was the kind of definition of central limit theorem. You can look for it and Google it to understand it better. There are many videos out there can show you with kind of examples, interactive examples, and then you will understand it much better. Okay, so what was the large number, law of large number? It says the result of performing the same experiment over and over and over in large number of trials must be very close to the expected value. For example, if we toss a coin 100,000 times and every time we write down the result, if it is head or it's not head, eventually after 1,000 times, if we look at the data, we will see that this result is diverging to an expected value, which is half of the time we observe head, if we have a large number of trials. And if the experiments are all independently. So these two are important. Large number of trial and the experiments are independently. Law of large number. So you can investigate this further and see what that says. Okay, so now what I want to do, I created this normal distribution, right? What I want to do, I want to experiment here and prove the law of large number, what's that? Central limit theorem. Central limit theorem. Okay, so what I'm going to do, I'm going to use the number generated there. What was that? This one. Okay, I will say we already generated 1000 numbers using this one. And then with this set, seed set. Okay, we know this. Okay, so what I'm going to do, I'm going to use this, find the mean of distribution, print this mean, find the mean of these random numbers, and then I'm going to find the standard deviation of these random numbers. Okay, this is the mean and standard deviation. Now, what I'm going to do here, I'm going to use for loop. Eventually, you will learn how to use for loop to create loops. Okay, so what I'm doing here, I'm creating an empty array. I will say for I in range 1 to 100. What range does? Do you remember? Range, let's see what range does. Range will create numbers from 1 to 100, right? 100 is excluded. Correct? I'm going to put that here. Creating numbers from 1 to 99. Creating numbers from 1 to 99. It says I in this range, means I starts from 1, then becomes 2, then becomes 3, then becomes 4, up to 99. For each of these numbers, I'm going to do this. I'm going to create a sample, and I'm going to randomly choose a sample of size 20 from the random numbers that I created here. For each trial, I get a random sample of size 20 from the random numbers I generated. Correct? So this is the part I said. If we take a sample of same size over and over and over and try this, let's say 100 times, try this 1000 times, then I find the average of the samples. How? By using mean method. So first I'm explaining this. I am calculating the mean of sample, right? and each time I put the mean of sample in this empty array. I calculate the mean of each sample of size 20, then I put that in the array I created. So the first time the mean I calculate goes index 0 of this empty array. The next time when I is 1, it will go to the index, when I is 2, it will go to the index 1, the average that I calculate for sample. Next sample will go to the next index, and then again the sample will have a mean, another sample will have a mean, and again it will store in this average in the next index up to 100 times, right? Okay, so I will do this. Each time, right? And then let's see what I will get. So at first, the average array I made is empty, and then at the end, when for loop is done, end of for loop, then I'm printing, the array. Oh God, where's the wrench? Here. Okay, so this is the average and the array I made. So this is the average of sample 1, average of sample 2, up to average of sample 100, right? 99 actually. Okay, so this is the one. Now I don't need to print it out. I just wanted to show you, right? Okay, so what I'm going to do, I'm going to create figure and axis using PLT subplots with a fixed size of 6 and 5 with DPI resolution of 120 with share false. Actually, I don't need that anymore. I don't need this one too. I'm going to plot a histogram of all these averages that I created, and then I'm going to say let's create 50 bins. Let's color it dark blue. Let's that's it. Okay, so this is the averages for 100 samples. Look at this. Well, in compared to the 1000 random numbers I had, so normally, usually our population is way bigger than this, right? Let's say we have 5,000 people, right? So now we have the averages. So what this means, means two of samples had the same average, which is falling here. One sample had average equals 0.4 and more samples had average around this area, negative 0.1, right? Okay, so this is still not a normal distribution. This is still not something that I wanted to show you. What I wanted to show you, this is the mean of population. Population was all these random numbers. 5,000, let's say, random numbers, right? And the population has this mean. Mean of population. Right. Standard deviation of population. Okay, so the mean of population was 0.0055, and now the mean of averages must be around this one, 0.0055. It's not like that yet. Why? Because the number of samples I chose here was not that big. Let's say I try this 1,000 times, means I create 1,000 samples and each sample will have an average, right? Then we will see this distribution. So now this is the distribution based on 1,000 samples. And then as we see, it's almost normal, right? And then the mean of this normal distribution, which is the midpoint, is closer to 0, which is our mean of population, right? Let's create 2,000 samples, which means I'm increasing the number of trial, right? Based on law of large number. Then look what happens. As I increase the number of trial, number of samples, this is getting more and more like a normal distribution with the average more and more closer to 0.055. So what is the standard deviation of these averages? The standard deviation of these averages will become divide by np.sqrt of n. What is n? N is the 2,000 samples. I will bring this here and print it here. And then this is the formula for the standard deviation of averages. So a standard deviation of averages is always different from a standard deviation of population. This will be much smaller based on the sample size, the number of samples, not sample size. Sample size was this one, right? So now on you, when you're watching this, you want to experiment on your own and see how it changes and how you can, kind of change the values. You can change the size of each sample and see based on the size of each sample how the average will change. But the most important is the number of samples, 1999, right? Okay, good. This is about central limit theorem. So now that we know this, I want to create one more thing. I'm going to copy the whole thing, bring it here. I'm going to delete all of, actually let it be here. I'm going to remove this because now I want to create two different loops, because I want to create two different samples. So this is the first one, this is the first one, and this is the second one that I'm creating. This one. Why this one is red? Okay. Let's see. Okay, so now I'm creating two different averages. And I'm going to draw both of them. This is 0, 1. This is 0, 2. And then I will have, oh, both of them now are dark blue. Let's create a red one. Oh, red blue. Dark red. Okay, so here it is. Now I have two different experiments. One is averages that of a sample, one set of sample I created here, and then the next one is for another sample, another set of samples that I'm creating, right? And then here I can choose the alpha equals 0.5, which makes the colors more kind of transparent. We will see the red on top, the blue is here, and then that is the shadow of blue. So just I wanted to show how I can create two different samples. And then let's say this one is 1000, the other one is higher, right? More sample. See how it changes? So when I have a smaller number of sample, look, I will have less frequency, right? And then the next, the other one has more number of samples, it is more frequent. And yeah, if we create two sets of samples from the population with different number of trials. Okay, so that's it, and let me see what I have for you. So I can show you another one using this is just describing different kind of package using Seaborn package, import Seaborn as SNS, and then I'm going to use plt dot subplot plot, and only I'm going to use figure size equal 6 and 5 and DPI resolution of 120, and then I'm going to SNS dot attribute is dist plot. So this is the way I can create a distribution or density curve above each of these curves. I'm going to use averages 0, 1, and what was that? 0, 1 and 0, 2. 0, 1, and I'm going to choose the number of bins equal 50, and then I'm going to color it. Color is equal to dark, or no, this one, Dodge air blue, and then I'm creating another one using another color, pink. What did I do? Let's see. Oh, it's another value. What was the pink? Let's try deep pink. Okay, good. Here. So as you see, we will have a distribution or density curve above each of these graphs. And the sizes are good. Everything is fine. Okay. I use this package to show the density curve for each of the distributions. I could get this one and see what happens. Let's leave it for you if you want to experiment on this. Okay, so for this lecture, I have actually a question for you. So the question. Okay, participation question for this lecture. Let's say for this one, for these averages, if there are 2,000, okay, what you are going to do, you are going to use the one that I have set a seed, like this one. So I want to see what is the answer for all the students. It should be the same. So we are going to use the seed. Remember, I'm talking about this graph that I have a seed 2020, right? I want you to go back to the previous lecture. Find the H. What was H? H was the width for each beans. How do you calculate that? You should figure that out on your own. But I will give you a hint. First, you should find the first quartile for these averages. Actually, that would be difficult if you find the first quartile for the averages. For this one. Okay, for this one. So for random numbers, I want you to find the first quartile, third quartile, find the IQR, find minimum, maximum of random numbers. So we have seed. So all the random numbers created must be exact same, right? With same mean, same max. And then you are going to calculate the H, which is the width of each bean. And then you are going to calculate the number of beans based on that H. So that will be the participation point for this lecture. Take care of yourself. I will come back with more graphs and visualization.